How are y'all doing today?
Doing
Doing well.
All right, so today we are going to talk about linearity and superposition. And linearity and superposition can be broken up into two distinct properties, the homogeneity or scaling property and the additivity property. So I've not really prepared an example problem per se, but we're going to work one of your homework problems because it is a great example of where you can use the scaling property to make, I wouldn't say it's an entirely difficult problem easier, but it's a great way to exploit that property. So hopefully you all can see the problem that I have down. And so we're asked to effectively look at the circuit in three different ways. For part A, we're told that if the current IX is 310 milliamps, to find the voltage Vs on the left-hand side of the circuit. In part B, we are told if Vs has a particular value, to find the value of Ix, and then in part C, to calculate the ratio of Vs over Ix. So let's look at part A. And part A is actually the only part that we're going to do any circuit analysis whatsoever on. Everything past part A we're going to take care of just using the principles of superposition. So if the current Ix has a known value, how is that piece of information useful? Anybody got any ideas?
Once you know the value of the current, then you can. It's the same thing across. If you go through that node the rest of the way, it'll come back up on the other side. Is that right?
So if we know the value of this current Ix, then I would argue that we know the value of this voltage drop, right? Because that current Ix is flowing through the 10 ohm resistor.
Yeah, that makes sense.
Opposition. Okay, so if Ix is, I believe I have it written down as 310 milliamps, and we multiply that by 10 ohms, that should be 3.1 volts. So what's the voltage drop over the 8 ohm resistor then? Any ideas?
Would it also be 3.1?
You're correct, but I would like for you to explain why that's the case.
I thought you would use Kirchhoff's voltage law around that
You could
close
do that.
loop.
Yeah, so if you did a simple voltage KVL loop around the loop containing the 8 ohm resistor, the 10 ohm resistor, and that short circuit, you would find that it's 3.1 volts. You could also observe that the 10 ohm resistor and the 8 ohm resistor are in parallel. Either way, you're going to get the same result. So now that we know the voltage drop over the 8 ohm resistor, we could figure out how much current is flowing through the 8 ohm resistor as well, right?
Yeah, Ohm's law.
Yep, so Ohm's law, 3.1 volts divided by 8 ohms. Over here. 387.5 milliamps. So do we have enough information to determine the current flowing through the 6 ohm resistor?
Wouldn't your voltage still be the same? So you just do 3.1 volts divided by 6 amp or 6 ohms?
So in order for the 6 ohm resistor to have a 3.1 volt drop over it, it would have to be in parallel with the 8 ohm resistor and the 10 ohm resistor. And that isn't the case. So let me explain why. So we have this node, and we have this bottom node. The other side of the 6 ohm resistor, however, is an entirely different node. So if the 6 ohm resistor isn't in parallel with the 8 ohm resistor and the 10 ohm resistor, there is no reason to assume that that voltage drop would be the same. And let me identify my other node too, just for the heck of it. So, any other ideas on potentially determining the value of the current flowing through the 6 ohm resistor?
Wouldn't it be equal to the current flowing through the 8 ohm plus the current flowing out of the 10 ohm?
Yes, that's exactly right. So if we apply Kirchhoff's current law at this node, we can find that the current flowing through the 6 ohm resistor is 387.5 milliamps, the current flowing through the 8 ohm resistor, plus 310 milliamps, the current flowing through, oh, excuse me, the current through the 10 ohm resistor. So that's going to look like, let's see, 387.5 plus 310 is 697.5 milliamps. From this, we can find the voltage drop over the 6 ohm resistor. 697.5 times 6, 4.185 volts. And now we have enough information to find the voltage drop over the 4 ohm resistor. How would we go about doing that?
Looks like you would just use KVL again.
Yep, so KVL, absolutely right. So in this problem, all the analysis that we're going to be doing is effectively flip-flopping back and forth between KVL and KCL with an Ohm's law equation thrown in every now and then to give us a little bit more info. So 4.185 volts plus 3.1 volts is going to give me 7.285 volts. This allows me to calculate the current flowing down through the 4 ohm resistor, which is 1.821 amps, with some rounding there. Now I can find the current flowing through the 2 ohm resistor by applying KCL at that light blue node. So that current plus 0.6975 amps gives me 2.59 amperes, which allows me to calculate this voltage of 5.0375, so 5.038 volts. I can add that to that 7.285 volts. And find that Vs is equal to 12.322 volts. 3225. So that would be my final answer for part A. Ix is equal to 310 millivolts. Effectively, I worked backwards through the circuit from right to left, applying Ohm's law, then KCL, then KVL, then Ohm's law, KCL, KVL, etc. So that wasn't particularly difficult per se, it was just rather tedious. So in part B, we are asked if Vs is equal to 142 volts, find the value of Ix. So what I'm going to do is I'm going to effectively make a kind of a table here. So we know that when Ix was 310 milliamps, Vs was 12.3225 volts. Our goal now is whenever Vs is 142 volts to find this value of Ix. And we can do this performing no more circuit analysis at all, okay? So what I mean by that is 142 is 11.5236 times our original voltage of 12.3225. So what that means is that since we have a linear circuit, the current observed when our voltage is 142 volts should just be 11.5236, et cetera, times our 310 milliamps. So times 0.310, 3.572 amperes. Because if we scale our input, the source voltage, by a particular factor, then we have to scale our output current, the value of Ix, by that same factor. So we've worked this second part of the problem, finding Ix for Vs is equal to 142 volts without actually doing any extra work whatsoever. So that's a pretty interesting relationship. As it turns out, you could really solve any circuit using only like 1 volt and 1 amp sources and then scale everything based on your results from that and still be able to work literally every circuit that we're going to deal with in this class. So let's take a moment and look at in-class assignment number 5. Okay. So this problem is going to use the additivity principles of linearity and superposition, as well as the homogeneity principle that we just went over. So it says for part A, to determine the contribution of the 1 amp current source to the voltage Vx in the circuit above. So what that means is that we are going to have that 1 amp source on and our voltage source off and analyze the circuit in that way. So how do we turn a voltage source off? Did anybody watch the lecture?
It just becomes a short.
That's absolutely right. So we're going to short circuit that 5 volt source. So let's redraw this guy down here. So for part A, we're going to have a 17 ohm resistor, a 1 amp source, a 20 ohm resistor, let's see, 10 ohms, 7 ohms, and a short circuit, like so. And Vx is defined as the voltage drop over the 20 ohm resistor, so this will be Vx single prime. All right, so is there any simplifications, further simplifications to this circuit that we could make? Let's start.
Can you eliminate the 10 ohm and the 7 ohm resistor?
I can, but would you explain why?
Because whenever the current has a more efficient way to flow instead of through those resistors, because both nodes or both ends of the resistor are on one node.
Right, okay. So the 10 ohm and the 7 ohm resistor are what we would call shorted out, meaning that they're placed in parallel with a short circuit. So another way to, the way that you described it is actually perfectly adequate. But another way to think about that is going back to the definition of a short circuit. So a short circuit has a resistance of 0 ohms, right? So what we have is an equivalent resistance, REQ, where we have 1 over 10 plus 1 over 7 plus 1 over 0 to the inverse. So this is going to look like 1/10 plus 1/7 plus infinity, which is going to be infinity. And we take that to the -1 power, our equivalent resistance is 1 over infinity, which is 0. So this 10 ohm resistor doesn't do anything because it's shorted out. The 7 ohm resistor doesn't do anything either, and we're just left with that short circuit. So how can we go about finding the quantity Vx prime now?
I found the current over the 20 ohm resistor, and then just did Ohm's law.
Okay, so you're suggesting we find the current flowing through the 20 ohm resistor and then apply Ohm's law. Nothing remotely wrong with that. How did you find the current flowing through the 20 ohm resistor?
Looking at my work, they're just in parallel now. And so I did, well, no, I'm still getting used to the current division.
Okay, so that's what I had assumed you had done. So you applied
Yeah.
current division and then Ohm's law. So I'm going to do that all in one step real quick, okay? So Vx prime is going to be our current 1 amp multiplied by 1 over 20 ohms times 1 over 17 plus 1 over 20 ohms, and then you multiplied it by a factor of 20 ohms, right?
Yep.
So I use current division and then I use Ohm's law. That is actually the exact same thing we would get if we multiplied our 1 amp of current times, 1 over 17 plus 1 over 20. So effectively multiplying the current by the equivalent resistance or doing current division and then multiplying by the resistance gives us the same result. So in this case, with only 2 resistors, I would argue that current division might be overkill, but it's good instincts that you're actually recognizing that that's a viable tool to use. So I'm very pleased there. It's just in this one particular instance, maybe just using Ohm's law would be a little bit more efficient. So to that end, we're going to have 1 amp times, let's see, 17 times 20 is 340, divided by 17 plus 20 is 37. So 340 over 37, 9.189 volts. All right. So part A is taken care of. For part B, we're asked to determine the contribution of the 5-volt source to the voltage Vx in the circuit above. So that means the 5-volt source is going to be on and the 1 amp source is going to be off. So how do we turn off a current source?
It's just going to be an open circuit.
Open circuit, absolutely correct. So let's see. I'm going to have my 17 ohm resistor here. Here's my open circuit where my current source was. Here's my 20 ohm resistor. This is a 10 ohm. This is a 7 ohm. This is my 5-volt source. And this quantity will be Vx double prime. So how could I approach finding Vx double prime in an efficient way?
When I was working this one last night, I must have done something wrong because I got negative 3.703, which is just one off of the value up there, but I couldn't really find my mistake.
Okay.
So,
So how I would approach this one would be, first I'm going to kind of notice something. Like I've already noticed it, but I'm going to notice it on your behalf, as it were. So that's one node. That's another node. And just for the sake of argument, here's a third node. So voltage is, by definition, the potential difference between 2 points in a circuit. So the potential difference between this orange node and this green node is 5 volts with positive polarity on the top. So even though there are these two 7 ohm resistors and 10 ohm resistors here in series, the in parallel, the 20 ohm resistor that is in series with the 17 ohm resistor, we know that there is a total voltage drop of 5 volts over those two elements. So this is a great place to use the concept of voltage division. So Vx double prime is going to be negative 5 volts times the resistor that we want the voltage drop over, which is the 20 ohm resistor, divided by the total series resistance seen by the 5-volt source, which in this case would be 20 ohms plus 17 ohms. So that's going to be negative 5 times 20 over 37 is negative 2.703 volts. So one thing that I want to make super clear here is where this negative sign came from, okay? So the circuit that I effectively just looked at, the 10 ohm resistance and the 7 ohm resistance don't really contribute much of anything. So I'm really looking at it from the perspective of, here's the 5 ohm resistor, here's the 20 ohm resistor, and here is the 17 ohm resistor. So it should be fairly obvious the current is going to flow counterclockwise around this loop, meaning that we should expect, so let's call this guy V20 and V17, the following polarities to make these resistors absorb power. Now the issue that we're having here is that the quantity Vx double prime has the opposite polarity as what we would expect, and so that's where that extra negative sign comes from. I think I addressed that in one of the example problems that I worked on the pre-recorded lecture, but I just want to make sure that I cover it well because it's going to potentially trip you guys up. All right, so let's look at part C. Did I run out of room? I did. All right. So part C says, using the results of parts A and B, determine the voltage Vx with both sources on. So instead of going through the trouble of analyzing this circuit with both sources on, we can exploit what's called the additivity property So part C tells us that Vx, the voltage drop over the 20 ohm resistor with both sources on, is going to be Vx prime, the voltage drop over the 20 ohm resistor with the current source on and the voltage source off, plus Vx double prime, the voltage drop over the 20 ohm resistor with the voltage source on and the current source off. So we can just add our results of parts A and B. And we find that we get 6.486 volts. There we go. So that's one way that the concept of linearity, specifically the additivity property, can be used. So this circuit with both sources on, it wouldn't be wildly difficult to do, but analyzing the circuit with only one source on at a time definitely made it very, very easy. So that's one way that we can effectively break down our circuits to get analytical solutions in a simple and efficient manner. Part D is all about exploiting the homogeneity or scaling property. So part D says, if the voltage source were replaced with a 3-volt source, positive polarity on the bottom, and the current source were replaced with a 2.5 amp source, direction up, use the properties of linearity to determine the value of Vx under these conditions. So let's look at part D real quick. So we're going to find what I'm going to call Vx new. All right. So what scaling factor is being applied to our voltage source in order to make it a 3-volt source, positive polarity on bottom?
-3/5.
Right. So that means we would just apply -3/5 times Vx prime. What scaling factor is being applied to our 1 amp current source to make it a 2.5 amp current source, direction up?
2.5.
Yeah, 2.5. Positive 2.5 times Vx double prime. And so now we're going to get a numerical answer that's absolutely correct, doing no more circuit analysis. That's the beauty of linearity and superposition. So let's store this. So -3/5 Vx prime plus 2.5 Vx double prime is equal, well dang it, I got a different answer. Let's see. So what did oh, I see what the issue is. This should be Vx double prime and this should be Vx prime. That's my fault. Because Vx double prime is the one where the voltage source is on, and we talked about scaling the voltage source first. And then Vx single prime is the one with the current source on. So that's my fault. -3/5 plus, there we go. 24.595 or 459, whatever volts. All right. Let me think what I want to talk about now. So this is an old exam problem that I gave, gosh, I think my first quarter teaching here at Tech full-time on using superposition. And so it's a word problem. There's no circuit whatsoever associated with it. But I'd like you guys to give an attempt on seeing if you can figure out what the answer is. So the problem says, a student is analyzing a circuit that contains an independent voltage source, Vs is equal to 4 volts, and an independent current source, Is is equal to 20 milliamps, using superposition. If the student determines that a current of 15 milliamps flows through a 3 ohm resistor when the voltage source is zeroed or turned off, and a current of 7 milliamps flows through the same resistor when the current source is zeroed or turned off, what would the total current flowing through the 3 ohm resistor be if Vs were changed to 2 volts? So does anybody among you have an idea of how we would approach a problem like this?
This may take longer, but I essentially try to draw out the problem so it's a little bit easier to picture in my head.
So we don't know anything whatsoever about the circuit other than that there is a resistor, a 3 ohm resistor, a voltage source, and a current source, but we don't know how they're connected. So I'm not sure that there's enough information for you to draw anything here with regards to drawing a circuit. So what
Well,
I would,
superposition is basically just the additive property. And so you can just use that.
okay. So yeah, what I'm suggesting, and I think it's, well, crap, I can't draw on this. Create a table, much like we did before. Inputs and outputs, right? So when we applied a 4 volt source by itself, our output was what? Read the problem. What's our output? So what's our resistor current when the current source is turned off?
7 milliamps.
7 milliamps, all right. When we have our current source on by itself, so we apply an input of 20 milliamps, what is our output current?
15 milliamps.
15 milliamps, all right. So what we're trying to find is what happens when we apply 20 milliamps and 2 volts.
So could you scale down the 4 volt input and therefore the 4 volt output and then add that to the 20 milliamp output?
Exactly correct. That is exactly what I want you to do, right? So we're going to get the full output from the 20 milliamps, which is from the 20 milliamp input. So we're going to have 15 milliamps plus. So applying 2 volts is 1/2 of our 4 volt source. So we should have 1/2 of the corresponding output. So that's 15 plus 1/2 of 7 is 15 plus 3.5 is 18.5 milliamps. So we can even work problems where we're just given partial information and figure out how the circuit is going to behave using the superposition principle, right? And this one is another example that's using both the linear, the scaling property, which we had to use here at the end, as well as the additivity property. So I'm trying to impress upon you guys how powerful this tool of superposition can actually be. So anyway, I can't really think of anything else to talk about. Does anybody have any questions or anything about?
I'm good.
I'm fine.
Problem or anything else? Okay.
Yeah,
All right. Well, it seems like at least a couple of you guys actually watched the video, so I'm thankful for that. And it seems that some of you actually did the in-class assignment prior to showing up here. So that's also very good stuff. So I'm slightly less, I wasn't mad yesterday per se, but I'm pleased with the effort that you guys are putting in. So unless anybody has anything else, I think we can wrap up for today, and I will see you guys on Thursday, where we're going to be talking about nodal analysis, which is going to be a very, very powerful tool for you guys to be able to use in circuit analysis.
Hey, Dr. Hartman, did you say that we were going to have at least one review day before the test on June 2nd?
Yes. Let me look.
Okay.
So I believe I have it set up to where we have a review day prior to every exam.
Okay.
But I can double check that real quick. So let's stop sharing that. Start sharing.
I think it's on June 30th, if you said it's the class before the exam.
Let's look at what I've got on the syllabus. Yes, so the exam is on Thursday, July 2nd. So the Tuesday prior to the exam is a review day. One thing I guess that I should also point out, the material for exam 1 is going to stop at the practical sources lecture. So Thevenin and Norton equivalent circuits will not be on exam 1.
And how long are the exams again? I kind of want to time myself in the practice exams.
Okay,
Before.
so the practice exams are 35 questions, and I typically give 2.5 hours to do them, but because of the online format and all that crap, I've been giving a full 3 hours to take care of them. So I believe I will continue to do that. So you should expect 35 questions, just like the sample exams that I've posted online. The first 10 questions are, in my opinion, should take you roughly 1 minute or less to do. And then the remaining 25 questions are actually involving detailed analysis and things like that. So they should be making up the bulk of the things you're spending your time on. You will have 3 hours with which to complete the exam. The exam will be offered online on Moodle using what's called the Respondus Lockdown browser. Did any of you have an opportunity or anything like that to use that last quarter?
Yes, sir.
For math tests.
Okay, so just to be clear, the exam is going to require the use of a webcam. So you've got a couple of weeks to work out the logistics on having some sort of webcam or whatever available to use for the test. And that browser is going to lock you out of all other applications and stuff on your computer until you finish the test. These tests are closed book and closed notes, no equation sheet or anything like that. My expectation is that you guys actually learn this material, not just write stuff down and then half-ass it.
Alrighty.
Any other questions regarding the exam or anything else?
One quick question. You said practical sources is where we stop for exam 1, right?
Yeah, so practical sources will be the last information included on exam 1.
Okay. All right. Thank you.
Yeah, so you'll have, so I'm happy to answer questions regarding the practice exams during that review day and relevant questions regarding the practice exams during these class meetings as well. So if you have any questions about stuff on material that we've previously covered, I'd be happy to answer questions. But if it's on material that I have not yet covered, then I would table those until we get to that material. Otherwise, it's going to get confusing.
Hey, Dr. Hartman,
Yes, sir.
could you possibly go back to the web work problem at the beginning? There was something I had missed from it. I was just...
Sure. Any question about it, or you just missed copying something down?
Yeah, I just missed copying the chart down because I was
Okay.
curious of how you did that.
Yeah. So I like to just make simple tables like this because it helps me. I know it's probably awkward looking at a circuit from a system level perspective where we're only concerned with inputs and outputs, but it can be a very valuable tool, as I hopefully have shown in the examples I've worked today.
Yeah, no, they look like they organize everything pretty well too. So.
Yeah. All right, any other questions?
No, sir.
Awesome. Well, I will see you guys on Thursday, where we'll talk about nodal analysis.
Excuse me,
yes,
Dr.
sir.
Harvey. I actually did have a question, not particularly related to the exams, but kind of.
Okay.
Is there any possibility of us transitioning to like any kind of in-class thing during second session?
So the way that it has been explained to me is that all of the first summer session classes are fully online, and all of the classes that are taking the full duration of the summer are also fully online. So I cannot make you guys do things in person. That being said, I don't know if I'm going to be on campus every single class day for effectively when the second summer session was going on. Like this week, I'm just trying to stay at home so I don't put too many miles on my new car. But I would not be opposed to doing some things in person as long as we're able to limit contact and practice safe social distancing and all that crap. Because I have a chronic respiratory illness that I've had since I was a baby, and am not looking forward to ever catching the coronavirus. So
Yes, sir.
yeah, I'm willing to meet on campus to help people with things. And if there needs to be, say, like a not using the Respondus lockdown browser, like if some people would prefer to take a paper version of the test or whatever, I can try to facilitate something like that. It just, yeah, I need to know what you want to do, and then I'll figure out whether or not I'm willing to do it.
Okay, yes, sir. Thank you.
Yep.
What happens if like we have some issues like with the Respondus? Are we allowed to like maybe take the test later in the day? Like, I'm just curious because it may go wrong.
I believe the way that I'm going to have it structured is effectively like a common night exam, like is usually done. That being said, I typically give my cell phone number. So like last quarter, what I had to do was give my cell phone number out to all 100-something students, and roughly, I'd say somewhere around 20 students out of those 100 students had issues, some sort of issue with the exam, whether Respondus just wouldn't let them in or something like that. So what I would have you do is text me or call me, and we could talk about it. You know, if it's a problem on Respondus's end, I can reset your attempts and this, that, and the other. If it's a problem on the end of your internet service provider, I understand that you know, that's out of your control, and we can work on having you take the test at an alternative time or something like that. But it's on a case-by-case basis, I guess. So the expectation is that all of you will take the test at the same time, using the Respondus lockdown browser, so that minimizes the opportunities for collusion and cheating, and, you know, letting other people know what's on the exam and have extra time to study, because it's unfair to those people that are taking it.
Because I had a problem with, I think on one exam with freezing when it came to like the Respondus. I don't know if it was the internet or the software, but that was a problem for me last quarter, at least one time. So
Yeah, I know that like some people are able to effectively reset their browser and jump back into the test, and other people, it seemed to lock them out of the test, and I had to reset their attempt. So what I would definitely suggest for you all to do is, well, you're going to need scratch paper regardless, but make sure that you write down the answer to each problem as you solve it, because if I have to reset your attempt, it would be terrible for you to have to actually go through and rework all those problems. Resetting the attempts, meaning that I have to completely zero out all of your submissions and stuff like that, wasn't something that I had to do an awful lot, but it did come up. And I know that it's super frustrating to you guys, and I wish I had a better solution, but I really don't. So I don't know what else I can do. Yeah, like I said, if there's any issues with using the lockdown browser, we'll address them, as they come up. I hope that a lot of the issues that students saw last quarter in particular was that there was a lot of people using the browsers at the same time. And since this class is smaller and it's also during the summer session, there's a less likely chance of overlapping with other exams and things. So hopefully we'll see significantly less issues this quarter, but I can't discount that possibility. All right, any other questions?
No, sir, I'm good.
All right, well, thank you guys for showing up and being responsive and participating today, and I will catch you on Thursday. Have a great rest of your day.